You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Pedro J. Alvarez, Professor of Engineering at Rice University. I'm going to be talking about Venus flytrap-esque spheres that catch and destroy bisphenol A, BPA, which is a synthetic chemical used to make plastic. So, Pedro, thanks for coming today. How you doing?
Pretty good. It's nice talking to you.
Yeah, I've, for people that don't know, I've heard about bisphenol A and that it's used in a lot of products and it's quote unquote bad for you. But can you talk about a little bit about it and why is it bad for human health and the health of other organisms?
Sure. So bisphenol A is one of these contaminants of emerging concern that simulate hormones, and basically they act as endocrine disruptors. And bottom line is that they affect our fertility, not only humans, but also, of course, aquatic organisms or other organisms that might be exposed to them. And that, of course, affects reproduction rates and when you reach puberty and things of that. So they're pretty bad in the environment.
Okay. So what about in adults? Do they disrupt hormone regulation and cause them problems, or is it more for children or pregnant women?
Yeah, well, in theory, everybody, of course, could be affected depending on the duration of exposure and the dose to which you're exposed. But it certainly some populations, such as children approaching puberty, will be more susceptible and therefore more impacted by it. And the problem is that, our current infrastructure that is supposed to be removing these pollutants from water isn't just doing the job often. And the reason is because these contaminants are not regulated, and typically when you do wastewater treatment, for example, it's about doing it as cheap as possible, as long as meeting the existing regulations, but not necessarily going above, above and beyond what you should be doing.
The standard.
Yeah, that's right.
So what are the most common sources of BPA? Where does it come from?
Well, many industries use it, as you mentioned, as a plasticizer. For example, many of the soups, canned soup, may have, a certain plastic cover, and that may leach out some bisphenol A into the soup. But just about every plasticizer, every plastic, many of them have this compound or similar related compounds.
I guess, yeah, it's used to line the inside of cans, right?
Exactly, yes.
So I guess baby food and other things that come in a can that are eaten commonly would be a large source of BPA for people, right?
It is, exactly. And again, I don't want to raise an alarm because, the adverse impact depends both on the dose and the duration of exposure. So, sometimes it is difficult to discern or establish a clear etiology, cause relationship between, a certain illness and bisphenol A. There may be multiple things that might be contributing to that illness besides bisphenol A, but nonetheless, it's important to take a proactive approach to risk management and minimize unnecessary adverse unintended consequences.
Right. Okay. I gotcha. What is BPA being replaced with, and is it any better?
Well, there is this is an area I'm not fully, conversant in. I know that there is significant interest in prevention of these things and green chemistry. And overall, we are trying to, as you know, use less plastics. So one of the most important parts of the solution is controlling demand and use, issues related to behavior, issues related to policy, rather than in the domain of technology. A lot of times the best solutions are not technologically, to be honest with you.
So what's the solution that you've come up with where it mimics the Venus flytrap? Tell me a little bit about it.
Well, sure. So we basically recognize that there is a need for advanced water treatment processes that can take care of these pollutants that current treatment technologies do not adequately treat or remove. And I noticed for a while that there was a significant interest in academia and in research on photocatalysis, the idea of using light to excite materials that generate oxidants, what we call reactive oxygen species, such as hydroxyl radicals in this place that attack this recalcitrant pollutant. But I saw this big disconnect. These people are very excited about it. They're publishing papers like crazy, growing exponentially the publications, and yet industry wasn't using photocatalysis. So we ask ourselves, why is that? And it turned out to be that it has to do with inefficiencies associated with the use of these oxidants that are generated by the photocatalyst, which results in very high energy requirements and a high operation cost. So we figured the solution to this is let's make the photocatalytic process more selective so that we don't waste treatment capacity on things that don't matter, and so that we target more specifically with more precision the target compounds such as bisphenol A. And then that will open the door to all these benefits, treating water without adding chemicals, potentially using a renewable source of energy to treat the water, in this case, the sun, and of course, generating less waste and bypassing the potential for generating this harmful disinfection byproducts that cause cancer. So we thought about how do we make it more selective? And then this is how we came up with. We decided to coat the photocatalyst with a benign, naturally occurring polymer called cyclodextrin that is innocuous, is harmless, and is very inexpensive. And it has a unique property in that it has a hydrophobic cavity that has high affinity towards these pollutants, such as bisphenol A, so that it can trap it close to the photocatalytic site where it gets zapped. So I call this trap and zap, right? You attract the pollutant close to where the oxidant is being produced so that it is used right there, in a productive manner, so to say, to destroy the pollutant rather than waste it on something else that doesn't matter, like naturally organic matter that doesn't harm you, or carbonates that are abundant in water that scavenge this oxidation power. So that's what it was about. And we call it a Venus flytrap because the photocatalyst was assembled in the form of a flower, but it's a flower that traps the pollutant, so that's why the analogy with the Venus flytrap.
Okay. So this will, where would you introduce this into a stream, let's say, would you use it in a wastewater treatment plant where you'd put this into the stream and it would adhere to the BPA and then precipitate out? Or how would you use it and what's the mechanism of action?
Right. So I would put it in a wastewater treatment plant right before the treated effluent is discharged to a river, for example, or wherever it goes, or to an irrigation field. And the idea is that not only you will be able to destroy bisphenol A, but other pharmaceuticals also that are bypassing and breaking through the treatment process, but also you will be able to disinfect quite efficiently and perhaps target these multi-drug resistant bacteria that are relatively resistant to chlorination. So it would be a multi-purpose polishing step. And of course, you want to retain the catalyst and reuse it so as to amortize its cost and reduce treatment costs. And that's why we made them into microsphere, relatively large particles that can be retained easily with a low energy filtration process that doesn't cost much energy. And the elegance here is that we made them large enough, but yet without sacrificing the enormous surface area that is largely responsible for the high reactivity that we see, for the high activity that we see. And the trick to maintain high surface area, despite the large particle size, was to make the particles out of nanosheets. So lots of nanosheets stacked up that offer huge surface area, but also offer the opportunity for easy recovery using low energy so that you can keep reusing them.
So what happens, does each particle adhere to one BPA molecule or multiple or thousands or millions, or like what's the ratio?
Multiple molecules could adhere to each of these particles, and the idea is that once they're zapped, the bisphenol A will be converted essentially to primarily CO2 and water. Of course, nothing lasts forever, and the coating, the bisphenol, the cyclodextrin coating, would eventually degrade. But the promising fact is that it can be very easily be regenerated or recoded in situ using simple technologies. So that's a positive aspect of it, that replenishing activity, as you have to do with pretty much any catalyst, would be something that is within our means to make it practical and feasible.
So, all right. So you'd introduce this into a waste stream. It would stick to multiple bisphenol A molecules. Then it would precipitate out. Then would you? I'm just guessing. Do you irradiate the waste stream, for instance, to destroy the BPA once it's adhered to the substrate or the catalyst, or do you precipitate it out first and then treat the precipitate separately?
Right. So the easiest way to apply it would be to use the existing infrastructure as much as possible. And many wastewater treatment plants already have what they call a UV contact chamber, where they have water passing through this small unit where you have ultraviolet rays shining on it to disinfect the water. And that's becoming more popular than chlorination because, as you know, when chlorine reacts with residual organic matter, it forms trihalomethanes and other nasty carcinogens that you don't want to form. So anyways, that UV chamber could be easily retrofitted to become a fluidized bed where these particles are floating around, they are suspended and trapping bisphenol A and other pollutants and degrading them. And right before it goes through the effluent, think about it, it goes through a screen that lets the water through, like a sieve, could be a microfiltration membrane. And then the microspheres, the Venus flytraps, stay in the reactor. So it's actually, you could precipitate them in a different scenario if you wanted to, but the easiest way would be just to keep them suspended.
Okay, yeah, but in the other way you said, I guess in that case, if they go through a sieve or a screen, then you'd have to backwash it to clean it periodically.
That is correct, yes. As we do with sand filters, for example, yes.
So why destroy the BPA? Is there a way to take it off the catalyst selectively and harvest it and
reuse it?
Is it best to just destroy it?
In theory, yes. I mean, in general, we environmental engineers view now wastewater treatment plants more as resource recovery facilities, and we try to recover energy and clean water and nutrients and whatever you can. But in many cases, the recovery is not feasible. In other words, it costs you more money than what you get worth out of. So that is the case in bisphenol. It would take just way too much energy and absorbance, and you would have to regenerate it and extract it and purify it. And it's so cheap to make, right? So that you're not going to get your money's worth. But, technically, it's certainly possible, just not feasible.
Okay. And then have you tested this? Like, do you have a bench scale setup, or how far along are you in this? Model?
So we have a large center with many universities where we're using nanotechnology and advanced materials to enable access to affordable clean water. Part of the center is that we create an innovation ecosystem where we invent something and we push it. And part of these innovation ecosystems are industries, companies, many of them global companies. And then if there is pull, then that's how you essentially cross the valley of death that many investors face. Water is a difficult space to innovate in because it's a very conservative industry, which, as I mentioned earlier, is trying to offer you water as cheap as possible. That it barely meets regulations for what the government tells you is not allowed to have in water. And since bisphenol A is not regulated right now in drinking water, then there is no regulatory pressure or economic pressure to do something about it. And if anybody is going to remove it, it's going to be just out of eco-responsibility or basically goodwill, if you wish. So that's one basically barrier that we may find in disseminating this technology. But
well, why do it then? Why not focus on something else in water, for instance, or in other streams that is regulated or is more harmful or respected as a pollutant?
Yes, indeed, and we are targeting, for example, multi-drug resistant bacteria that are difficult to disinfect using current approaches, as well as viruses and other things. But the good thing about this approach of this multifunctional photocatalyst that absorbs a pollutant and destroys it right there more selectively is that it can be used for a broad class of pollutants, including the pharmaceuticals. But also, it is part of being a little bit ahead of the curve. I mean, eventually people are going to have to regulate these pollutants because it just costs us much more money curing the diseases that they cause and the associated loss in productivity and healthcare costs than it would to prevent those diseases in the first place. Just much more economically to treat them than to let them go and deal with the consequences later.
Makes sense. Is this also a test of the methodology, that this could be applied to other pollutants, let's say in wastewater? Or
yes,
exactly.
Is it
just really for BPA, that's it?
Exactly. I mean, we're using the BPA as a socially relevant model of things that we could treat so that we can basically kick the tires in the system and learn better how to optimize the operation, the design of the material, the durability, and just learn more about the mechanisms and potential failure modes.
Well, in wastewater treatment, I know they do, I guess, what's called flocculation, where they're putting something into the water and it aggregates some of the solids or things that are in it, some of the pollutants are in it, and then they fall down in a settlement tank. What is that involved, and how is that different from what you're doing?
Sure, yeah, that's commonly done for drinking water treatment, where you first add a coagulant, as you said, compresses the charge of colloids that repel each other. And by doing that, now colloids are allowed to aggregate into flocks where they can sediment out. The problem is you're adding chemicals and generating huge volumes of sludge that are a headache to dispose of. And also when you add chemicals, there's some residual chemicals that you don't know what can do to you. For example, one of the chemicals we do add for coagulation is alum, an aluminum sulfate-based chemical that has been implicated with Alzheimer's. So it's better to treat water, in my opinion, using physical or catalytic methods that, number one, don't require you to transport potentially hazardous chemicals to far places, and number two, generate much smaller waste streams, if any. And that's why we're excited about photocatalysis and other advanced catalytic processes.
Yeah, actually, something obvious I just completely missed. So you want to use this on wastewater or drinking water? Why wouldn't this be used more on drinking water? Because that would have a more direct effect on people.
Absolutely, yes. So we are also doing it for drinking water, but this is more for people that are off the grid, people that are not connected to municipal drinking water systems. It's just an easier niche. And there's a lot of people in that situation. There's 43 million Americans that are not connected to a drinking water system. But we use a similar approach in Swaziland. Basically, this was a village that was using irrigation water for peri-urban irrigation and also for drinking that was very contaminated with pesticides and fecal matter and all that. Pretty nasty stuff. So we tested this photocatalyst there that was very small, small enough for you to carry it on an airplane with you. And it was capable of treating enough water for about 18 households. Enough for drinking and some simple garden irrigation, what we call peri-urban irrigation. So yeah, as a point of use device, a fluidized bed, packed with these kinds of materials will be certainly ideal.
Okay, interesting. So where are you at with the process? Is it going to be going first to people that are, again, off the grid in a home use kit for their drinking water, or is the first foray attaching it to a municipal plant?
I think that the easiest adoption would be, for example, for industry. If you're a facility that is an industrial facility that your wastewater is producing a lot of bisphenol A and related, let's say you're running a pharmaceutical company or something like that, then this advanced oxidation process will be ideal to use it on site before you discharge to the sewage system. You want to nip this problem at the bottom, so catch the source better. And then I think it will be easier to implement in wastewater treatment facilities because you already have the infrastructure in place and it's easy to modify it to apply this material and not only solve the pharmaceutical and endocrine disruptor problem, but also enhance your disinfection process. And of course, there will be less funding available for this, but nonetheless, it could have a higher impact in emergency response situations. You have for example, a disaster. You saw what happened in Puerto Rico, and they were left without lights and poor water quality for months. And this is the sort of thing that you can modify to work with a sunlight without the need for electricity. So you could have a huge impact there. I mean, I could see even the military using these such devices. I mean, you and I know that water is a major limiting factor to human capacity. Yeah. And we need sometimes technologies to bypass these huge challenges.
Okay. Well, very good. So what's the best way for listeners to find out more about your work and to see it, get put into production, to contact you with questions or ideas?
Thank you. Yeah, I would encourage them to visit our website for the NEWT Center, and NEWT stands for Nanotechnology-Enabled Water Treatment. And it's NEWTcenter.org. And it's a multi-university center, including Rice University, Yale University, Arizona State University, and the University of Texas at El Paso, as well as perhaps 20 large global companies that belong to the center. It's an effort funded by the National Science Foundation. And again, it's a very exciting innovation ecosystem, and it's just one of many, many projects, cool things that we're doing. So hope you visit us, and then, the contact information is provided there.
Okay. Yeah, we will in the show notes, no problem. Well, Pedro, thank you for coming on the podcast. I appreciate it.
It was a pleasure. Very nice talking to you.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.